Okay, so because I don't know if this is the test question at this late part of the course, and I don't know. So what I'm going to do is I'm going to solve a similar problem for you, and hopefully you can apply it to yours. Okay. Um, so I took this problem out of another textbook that I use, and what I'm seeing is first off, I want to find the ending behavior. I want to figure out what power function is like that. Well, if I were to expand out all these terms, I'm assuming that you've learned that you can find the leading coefficient, the leading term. If you can find the leading term, then that's going to be the function that rules way out of infinity. So for this one, what I'm going to do is I'm not going to expand this all out because that's a lot of work. But if I have t minus 3 times t minus 3, which means it's when I expand it and raise something to the second power, that means you FOIL it times itself. That's going to give me a t squared plus a lot of other terms that I really don't care about as far as the initial value. So then, if for this next one, it's going to be t plus 1 times t plus 1 times t plus 1, which is going to be a t cubed plus a lot of other terms that we don't care about. And then this last one just doesn't get expanded at all. It's just t plus 2. Now, if you now multiply all these together, we're going to do the t to the second times t to the third times t to the first. Well, then you add the exponents there. So what my ending behavior function is going to be the same as 2t to the 6th power. And that's the ending, that's the function that we're going to see way out at infinity if we zoom out. And you'll see that when I do the graph. The other thing they're asking me, I think, is the ending behavior. Usually we talk about what's happening as x goes out to negative infinity. We want to figure out what happens to y. And what happens when y goes out to, when x goes out to negative infinity and y goes out to, why am I saying y? I know why I'm saying y. Just a minute here. We want to figure out what happens when x gets really negative, when x gets really positive. Well, because this degree of that leading term is an even number, we learned at some point that it's going to act like a parabola. It's going to act like x to the 6th, or t to the 6th in this case, and with a bunch of wiggles and stuff going on in the middle, which we really don't care about. We're talking about the ending behavior. So as x goes out to negative infinity, y goes out to positive infinity, because that's what's happening. It's headed up like a parabola. And the same thing is happening when x goes out to positive infinity, y goes out to positive infinity there. So there's the polynomial function that's the ending behavior. And I'm describing what's happening out at infinity. Okay. Now they're asking us to find the x and y-intercepts. Well, the x-intercepts are where, remember, any place along the x-axis, in this case the t-axis, but the xt, we're going to use those interchangeably. It's going to be some x value and y is 0. So what I basically have to do is go back up to my function and ask myself, when is this piece equal to 0? Because if that piece is equal to 0, the whole expression is. The same thing here on this piece. When is that equal to 0? The whole expression will be at that point. And the same thing at 2. So what minus 3 is 0? Well, 3. So it crosses the x-axis or has an x-intercept of 3, 0. It also has an x-intercept of -1, because -1 plus 1 is 0. And then it has another x-intercept, or t-intercept in this case, of -2, because -2 plus 2 is 0. So those are the 3 x-intercepts that we're seeing. Now the y-intercept happens any place where, where's my pen? Happens any place where the graph crosses the y-axis, and that point is always x is 0, y is some number. So what we really need to do is find f of 0, or in this case k of 0. So what we're going to do is going to substitute in 0 for each of these t's. Here, let me get rid of some of this. Let's see here. So I'm going to do t and 0 minus 3 squared times 0 plus 1 cubed plus 0 plus 2. Well, I'm seeing 2 times negative 3 squared is positive 9. And 1 cubed is 1, of course. That's nice. And then times 2. So I'm seeing 2 times 9 times 1 times 2. That tells me the y-intercept is 0, 36. So we've done A and B without using any technology, just what we know. So then we got to figure out whether at these x-intercepts, whether the graph passes through or if it just touches the x-axis. Well, I'm hoping that you've learned sometime prior to now that if you look at the multiplicities, in other words, what degree are we raising each of these? Here, just a minute here. If I look at these multiplicities, that tells me how many times each of these zeros count, because it's supposed to have, I'm saying it's t to the 6, so they're supposed to be account for 6 zeros. Well, 2 of them happen here, 3 of them happen here, and 1 of them happens here. There's the 6 zeros. When I ever have a binomial squared, that's acting like a parabola. So that's what's happening at -3 or at +3. I mean, this graph, let's here, let me come back and so I can get my mouse. That means the graph, let me use this graph. That means at +3, this graph comes down and bounces something like that. Then it comes up, turns around, and then it's going to go up high, because then it's going to come back down and wiggle through at -1. So somehow it's got to go up, 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 turn around, pass through the y-intercept, come down and wiggles through it at -1. And I know it wiggles through because this acts like x cubed. And x cubed, if you think about what x cubed looks like, x cubed graphs come up, flatten out at the origin and head up. So that's what happens there. It flattens down and wiggles through. Then it's got to turn around somewhere, head up and pass through. Where is it passing through? At -2. First degree, it's only going to pass through it. So it touches the graph at x equals 2, or at x equals 3. It bounces, it passes through at -1 because it wiggles through, and then it passes through also at -2. Okay, so hopefully that helps. Now the next 3 questions are D, E, F, G, and H. I think they're telling us all to use a graph. I'm also noticing they're telling me to use 2 decimal points to find the minimum maximum. So this tells me it's okay to use technology because you haven't learned how to do this yet in pre-calculus. So what I did is I went out to Desmos.com and I graphed this function. And let me move this out of the way. So where the local extrema? Well, I kind of thought it would be here. I knew it turns at 3 at x equals 3. So that's going to be an extrema. That's a local minimum because it's decreasing, 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 turns around and it starts increasing, increasing, increasing. When I say it, I'm meaning y, right? So that's a minimum. I know this turning point up here will be a maximum because it's increasing, increasing, increasing. Right there, it's a maximum and turns. So there's the maximum value, and it happens at 1.602. There's a minimum value. It happens at 3.0. Notice it does cross through the x-axis at 0.36. So we're right. But that's neither a maximum or minimum, so I don't really want to talk about it. Now, at x equals -1 is interesting because even though it kind of flattens out, it's neither a maximum or a minimum. And in calculus, you'll learn something else about that point there, and we won't go into it here. But it is a special point, but it's just not a minimum or maximum. And then I see it turns down here. So when x is, or t in this case, or x, I guess, -1.796 or 69, that's where a minimum happens, and it happens there. And then, of course, there are only local minimums, maximums. There's no global minimums. I don't know if you've been talking about that yet, because this function goes on forever, right? It's a polynomial that well-behaved. There's no limitations on its domain. One thing I should do before I get too far with this, and this might help us want to answer one of your later questions. Okay, remember how I said that was the ending behavior? Well, if I zoom way out, you see how that blue line, that blue curve starts to overtake the red curve? Whoops, what did I just do? See how it overtakes? So really way out there, infinity. I mean, we could probably even change our window to make it look a little more convincing. What if I go from, let's see, what is that, 20? What if I go from negative 20 to positive 20? And then I change my, I'm going to go up with my y. What if we go up to, I don't know, how high will it let me go? You see how I get way out there? I mean, I'm way up at 7 billion. Is that billion? No, that's 80 million. And for the y, and you see how it's starting to approximate that curve. So that confirms that the ending behavior, that ending polynomial function, is the same as 2 to the x. 2 to the x, 2x to the 6, way out at infinity. Okay, what else do they want us to do with this question? They wanted us to, so we use the graph to find the maximum minimum, and I just use that right off the graph. Use the information to plan a complete graph by hand, label all intercepts and turning points. So what we're trying to do is I kind of did it down here, and all you have to do is come up with those. You'll have to figure out what those turning points are in your graph. Okay, you got to label the turning points, label the x-intercepts, label that y-intercept. Shouldn't be too bad. I think you know enough how to do that now. The domain, polynomials always have the domain of all real numbers, and we can see that. We can see that on the graph. Let's see, where is my graph? See, it goes out. There's no limitations on that domain. Here, let me turn off, because then there's no limitations on y. Well, there's a limitation. The range is a little weird because it doesn't go below that certain minimum. I mean, do we have to find the range? Just the domain. Oh, then use the graph to find the range. Well, you know that minimum here. Let me come back and take a look at. Let's do this. Oh, what was it? Zoom square. No, we don't want to zoom square. Let's see here. I got to go back to. Sorry, I got to go back so I get the mouse. Okay, this was what? Negative. I think I was able to do -5. Oh, maybe we need to go to -10. Let's go +10. Maybe we'll go to 20. I will go 10. Then the y values we have to change. That's way big. Let's see. Let's go from a negative. I don't know. Was it -50? I don't remember. To positive. Was it 250? I don't know. Oh, it's probably not too bad. So what's the range of this graph? Well, that's the absolute minimum, right? So the range goes from -4.778 up to infinity, because it goes forever up. That we know as x goes to -infinity. As x goes to -infinity here, right, let me move that. As x goes out to -infinity, as x goes out to -infinity, y also goes out to positive infinity. And as x goes to positive infinity, y goes out to positive infinity. So we know it's going from that -4 point whatever it was, that -4.788 up to infinity is the range, and the domain is all reals. What's the last thing we got to answer? Or where is it increasing and decreasing? So this function is, and you can kind of see it. See how the y is decreasing? It's decreasing until that turning point, and then it's increasing up until that turning point. Then it's decreasing. So you just got to write down the x coordinates there. You don't have to write down the y coordinates. So the x coordinate, it's decreasing from -infinity until negative 1.769. It's increasing from that number to that number. Then it's decreasing from this number to 3. And then it's increasing after 3. Okay, so that's how you use a graph to figure out increasing, decreasing. And I guess that's it. So hopefully that'll help you walk through that problem. If you want to come join me for a live session or somebody else for a live session and see the Screwdo schedule, glad to help you. Hope this helps you out.